Hi everyone. Today we're going to talk about power system operation and dispatch. Imagine you have a power system with a number of generation resources. Our goal is to find out how much active and reactive power should these resources exchange with the grid in order to supply the demand. We refer to it as PQ dispatch or active and reactive power dispatch. We want to make sure that we find a solution that results in the lowest cost. Obviously, meeting the demand is the most important constraint, but at the same time, I want to make sure that my generators only exchange active and reactive power levels that are within limits. So they are not supposed to inject active power more than the permissible range or reactive power outside of the permissible range. Further, no component is allowed to be overloaded. So transmission lines, transformers, they are not supposed to have currents or power flowing through them that is beyond their capacity. And last but not the least, the voltages within the system would have to remain within permissible limits, which under steady state conditions, that's typically plus minus 5%, or in terms of per unit, that means that no node voltage is allowed to go below 0.95 per unit or above 1.05 per unit. Take a close look at this problem. We have an objective function, which is cost of dispatch, and I want to minimize this cost. So I have an objective function that I want to minimize subject to a bunch of equality and inequality constraints. This is a constraint optimization problem. However, solving this problem is quite challenging. This is because a lot of things in a typical power system go through variations. First, let's talk about demand. Demand varies in real time based on secondly variations minutely or hourly. Renewable energy resources, likewise, they go through variations. Some of it short term, which would be secondly or minutely variations. Some of it could be long term variations in the range of hours. Some environmental factors, most important of which being ambient temperature, would go through variations typically on an hourly basis and can impact the maximum capacity of different components like transmission lines, transformers, PV panels, or even energy storage devices. Generation units also have availabilities that might change. For example, they might go through planned outages for maintenance purposes or unplanned outages due to disturbances. And every time one of these outages occurs, it could last a couple hours. And last but not the least, energy prices will go through variations daily, hourly, minutely. So when you look at all these uncertain parameters and data in the power system, we see that we have to find a solution for energy dispatch over multiple timeframes. We have to consider the variations that are minutely, hourly, and daily, which is why controlling the power system is one of the most complicated mathematical problems. Now, before we move forward, I want to clarify something here. There are two mechanisms for energy dispatch in power systems. One of them is power markets. Here you have a group of generators that compete with one another in a market. They place bids, and these bids are submitted to the market and overseen by an impartial independent market operator, which would then decide which bids are more attractive, and the ones that are accepted are conveyed to the generators to start injecting certain amount of power. This is what we're going to be talking about in the next lecture. So we're not going to be focused on this today. What we're going to be focused on today is the second mechanism, which is what vertically integrated utilities do. A VIU is an electric utility that owns majority of its generation and pretty much the entirety of transmission and distribution networks. Um, these utilities have the power, the means to regulate and dispatch their own resources. And that's what we're going to be focused on today. Now, a VIU goes through multiple steps in order to respond to all the different variations that I mentioned. So the first thing that we do is we run a unit commitment. In a unit commitment, the utility tries to find the units that need to be operational or committed during every hour of the day for the dispatch day. This is based on the information you have typically a day in advance about the demand, as well as any forecast for renewable energy resources. So obviously, doing this analysis a day in advance means that your forecast may not be very, very accurate. As you get closer to the dispatch day or the moment that you want to dispatch your generation resources, your information, your forecast is likely to be more accurate. This is when we run what is known as economic dispatch. Now, in economic dispatch, we already know what units are going to be committed. That information comes from unit commitment. Now, with more accurate information about the load, about renewable energy resources, we can then decide with more accuracy how much active power these resources would have to inject into the grid. Economic dispatch is typically run every, let's say, 30 minutes to an hour. But even between these solutions, between every 1 hour window, a 30-minute window, demand and renewable energy resources still change. So we're going to have to, again, go ahead and update the amount of power exchange between these resources and the grid. This is the job of optimal power flow. In optimal power flow, which is run typically every 5 to 15 minutes, we go ahead and further narrow down the amount of active and reactive power that generators would have to inject into the grid in order to control not just the frequency, but the voltage. Pay attention that in unit commitment, our question is only how much active power units need to be injecting into the grid. In economic dispatch, we again answer the same thing, only active power. In optimal power flow, we look into how much active power generators need to be injected and how much reactive power they need to be exchanging with the grid. So unit commitment is being a day in advance. Economic dispatch typically run every hour. Optimal power flow typically run every 5 to 15 minutes. But of course, you realize that even between those 5-minute intervals or 15-minute intervals where OPF or optimal power flow is run, demand and other factors within the grid might go through changes, hence impacting the operation. In that case, we need yet another entity that is known as AGC or automatic generation control to step in and respond to those changes by making sure that the frequency remains at or very, very close to 60 hertz. So with unit commitment, economic dispatch, optimal power flow, and AGC, we managed to respond to these variations that range from daily variations all the way to secondary variations. Typically, daily variations are covered by unit commitment, hourly variations are covered by economic dispatch, minutely variations are responded to by OPF, and secondary variations are responded to by AGC. This diagram perhaps helps you get a better perspective of the timeline. Imagine today is Tuesday and you want to dispatch your resources or determine what dispatch you want to have for tomorrow, Wednesday. So your dispatch day is Wednesday. Now, on Tuesday, the day before, what you do is you perform unit commitment. Unit commitment will tell you for every hour of the day on Wednesday, what units need to be committed or operational, and how much active power they would be injecting into the grid to respond to the demand. And keep in mind that information is based on the load forecast that you have a day in advance. Now, we are on Wednesday now. On Wednesday, what we're going to have to do is we're going to have to run multiple economic dispatch solutions, let's say one every hour, to know, for example, from the units that are operational at during hour one, how much active power they would need to be injecting into the grid. Here, I don't need to worry about determining which units are to be operational because that information is already provided by unit commitment. What I would do, however, is with more accurate information that I have about load forecast or the forecast of renewable energy resources, I can further fine-tune how much active power these operational or committed generators would be injecting into the grid. I repeat the same thing for hour 2, hour 3, 4, 5, 6, all the way through hour 24. But then between these solutions for economic dispatch, this is when I run optimal power flow. This is going to be run every 5 to 15 minutes to further adjust the amount of active power injection of these resources based on more accurate information that I will be getting, but also determining the amount of reactive power that these resources will be injecting with the grid. So one day before, we do unit commitment. During the dispatch day, every hour or every 30 minutes, we run economic dispatch. And then between those solutions for economic dispatch, every 5 to 15 minutes, we run an optimal power flow. If you look at a particular moment of dispatch that I'm showing here, one day in advance, you have unit commitment, 30 to 60 minutes before you run economic dispatch, and 5 to 15 minutes before you run optimal power flow. Let's take a closer look at these different solutions. In unit commitment, what I want to do is I want to know for the dispatch period, which is typically 24 hours, for every hour of that period, what units need to be committed and how much active power they would need to be injecting into the grid in order to supply the demand with minimum cost. Now, when you look at the cost functions, there are quite a few things. The most important of which, obviously, is the operation cost of the units that are online. But there are other factors. For example, maintenance costs associated to units that need to be going through planned outages for maintenance purposes. There are startup costs. These are the costs that are associated with bringing up a unit to operation. A large unit, think of it as a coal-fired power plant or a nuclear power plant. These are not plants that can be switched on or off just like that. They have boilers and turbines that would require a certain pressure and temperatures, and you would have to provide enough input energy to the power plant in order to bring those pressures and temperatures to the values that are required for the unit to be able to operational. During that time, the unit is not going to be able to produce any electricity. All the input energy to the unit is used up to bring it up to the operational status. This is known as a startup cost, and this needs to be taken into account every time you have a generator that has been off and needs to be turned on. Opposite of that is shutdown cost. Again, a large-scale power plant cannot be shut down just in one moment. You're going to have to lower the pressures and temperatures inside the boiler or the turbine gradually, slowly, in order to maintain the safety and security of the system. During that time, the unit is not going to be producing any electricity, but you will still be providing some input energy to it in order to gradually bring down those pressures and temperatures. That means additional costs that we refer to as shutdown costs. Another cost function could be cost of reserves in case you want to allocate a certain percentage of a unit's capacity to act as reserves. This model is solved subject to a variety of constraints, obviously the most important of which for steady state operation is that generation must meet the demand. We also have other constraints, for example, power flow constraints, typically for unit commitment. This is in the form of DC power flow. We have constraints for generation of different units, for example, limits on active power. We have limits on the amount of active power flow through lines and transformers. We have constraints associated to maintenance. For example, if there are certain hours of the day that certain units need to be shut down for maintenance. Some units have various constraints in terms of the number of hours that they have to be up or down, or operational or non-operational. This needs to be taken into account. Another important constraint is ramp up or ramp down constraint. Let's say a unit is producing a certain amount of megawatt at one time instance, and then you would want it to increase or decrease its generation by a certain amount for the next time period. Let's say you want it to go from 400 to 500 in 1 hour. That means that this unit would have to increase its generation by 100 megawatts in 1 hour. That megawatt per hour, that is known as the ramp rate of the unit. And units are limited by how much ramp rate they have. If a unit has a maximum ramp rate of, let's say, 50 megawatts per hour, it cannot go from, 400 megawatts to 500 megawatts over 1 hour. It'll take 2 hours for the unit to go from 400 megawatts to 500 megawatts. So those types of ramp up or ramp down constraints would need to be taken into account as well. And because we're looking into a dispatch during the course of a day, other constraints such as availability of fuel might be relevant also. And lastly, some unit commitment solutions, they also look into the environmental constraints in terms of how much pollution different generation technologies or different power plants would produce, and would consider that as a constraint to limit, for example, the amount of greenhouse gas emissions. Once we have done unit commitment a day in advance, we get into the actual dispatch day, and we would have to run multiple economic dispatch solutions. Now, for economic dispatch solution, what do we know? From unit commitment, we know at every hour of the day what units are going to be committed or operational. So that information is what we know. Given that information, our goal is to find the output of active power produced by these units to supply the demand at a minimum cost. The easiest formulation that I can present to you is shown here. Imagine you have a cost function for each generator G, which is a function of the amount of active power that is producing, which I'm showing here as P of G. So what I'd like to do is I'd like to minimize the sum of cost functions of all the generators that are committed for that particular point in time. These cost functions are typically quadratic, so they are in the form of a constant coefficient A of G plus another coefficient B of G times P of G, the amount of power injected, plus another coefficient C of G times the square of the power injected by that unit. This is the objective function that I'd like to minimize, but it's going to be minimized subject to at least two important constraints. One of them is the balance between load and generation, which says essentially the sum of generated power by all these different generators would equal demand plus losses. Further, no generator is allowed to inject active power beyond its capacity. So the amount of active power injected by each generator G would have to be limited by the minimum and the maximum levels. And of course, the economic dispatch problem can be more complex than that. For instance, we could incorporate DC power flow equations to make it a network constraint economic dispatch so that the capacity of different lines in the system are also taken into account. After we have run unit commitment a day in advance and economic dispatch, let's say every 30 minutes to an hour during the dispatch day, we would have to run optimal power flow between the solutions for economic dispatch. Here's the thing. In economic dispatch, as you saw in the previous slide, power flow is not explicitly modeled typically. So in most situations, we look into a very simple constraint of generation equals demand. Further, in everything I have talked about so far, unit commitment and economic dispatch, you notice that I only talk about active power and no mention of reactive power. Obviously, it's very important to also determine how much reactive power needs to be exchanged between those generators and the grid, because that would impact the voltage magnitudes at different nodes. So in order to address these two shortcomings, we would have to run OPF or optimal power flow. Here, our objective is to find the optimal amounts of active and reactive power output of every generating unit in order to supply the load, again, at minimum cost, subject to a bunch of other technical constraints. Let's take a look at this formulation. Of course, there are many variants for OPF formulation. This is one simplistic model just to give you an idea. Here, notice that, again, I try to minimize the cost, just like economic dispatch. The sum of cost of operation of different generation units subject to a bunch of constraints. This could be, for example, uh, the power balance equation for the nodes. For each node, the sum of power generated at that node minus the sum of powers consumed at that node would be the sum of powers that are exchanged between that node N and other neighboring nodes M. I have one such equation for active powers and another one for reactive powers. Then I will have the equation for the active power exchange between node N and M, two neighboring nodes, and likewise reactive power. This information comes from AC power flow. And as you can see, it's highly nonlinear. We have sine terms, cosine terms, and multiplications of different variables, for example, voltages, resulting in bilinear terms. Then I would have limits for generators, but unlike unit commitment and economic dispatch, where I only had limits for active power, here I have limits for reactive power as well. Further, I can have a limit of apparent power that goes through different lines or transformers based on the active power and reactive power that goes through those elements. And finally, I will have permissible limits for node voltages as well as node phase angles. By looking at this formulation and perhaps comparing it with economic dispatch, you realize how much more complicated this is. We have many more constraints that we would need to take into account. Plus, these constraints are nonlinear and not necessarily convex, which would make the problem more difficult to solve. And the last thing I wanted to talk about is to kind of point out how general the OPF problem can be formulated. In the formulation that I showed you in the previous slide, I assumed that the control variables for me are the amount of active and reactive power outputs of generators. But in general, we can have a more diverse set of variables. For example, we could also use OPF to control or find the optimum values for transformer tap positions. Or if you have phase shifting transformers, you can include their tap positions as a control variable as well. If you have switched capacitors that may be switched on or off depending on need, the status of the capacitor, the on-off status of that capacitor can be a control variable as well. In more advanced versions, sometimes people include fax devices like STATCOM or SVC and consider the reactive power injection of these devices to be another control variable. And lastly, we can look into load control in terms of either control of demand responsive loads, which go through voluntary load curtailment or load reduction, or an involuntary load shedding upon need. So these are the larger set of variables that could be included in OPF. So to recap what we talked about today, we looked into how vertically integrated utilities control their generation resources because of the variability in different aspects of grid, demand, the availability of generators, the variability in environmental factors such as ambient temperature, the variability in the amount of available energy, renewable energy resources, the variability in price, all these different uncertainties that go through minutely, hourly, or daily variations, we would have to divide this problem of PQ dispatch into multiple timeframes. First, we conduct unit commitment a day in advance to take into account the daily variations. Then we run multiple economic dispatch solutions to take into account the hourly variations. Then between those economic dispatch solutions, we run multiple OPFs or optimal power flows to reflect the minutely variations. And then we have AGC or automatic generation control that would take care of secondary variations in demand.